All right, let's get started. Danny's volunteered to give the prayer in Maori. I'm just kidding. Yeah. I used to be able to pray in Samoan because I served in a lot of Samoan wards when I was on my mission. So, yeah. Right. You want to do it in Russian?
I can.
Sure. Why don't you do it in Russian?
Наш дорогой Небесный Отец, мы благодарим Тебя за возможность собраться вместе сегодня, изучать математику. Мы благодарны за нашего учителя и то, что он помогает нам. Пожалуйста, благослови нам и помоги нам лучше служить Тебе во имя Иисуса Христа.
Amen. Thank you. Hey. All right. Devotional tomorrow. Elder Pace, he's the general Sunday school president. He will be speaking, so don't miss it. And any questions before we begin?
Yeah, actually, I had a question about Kramer's rule.
Oh, I'm glad. Okay. What is it? Is that your question?
It says that it's supposed to be for finding AX equals B solutions, right?
Yep.
So, but the solutions it gives are scalars, but X is a vector. So how does that work?
Yeah. Okay. So let me explain what Kramer's rule is, and then I'll. It's defined xi. If you think about x as a vector, then you can set up something like this, a determinant divided by a determinant that will give you the value for xi. So where it's each entry of x. Okay. So how do you do this? So this is a 2x2 system of equations. I can think about it as 2, 3, a minus 1, 2, xy equals 7, 0. So I can think about it that way too. So Kramer's rule is it gives you a way to solve for each individual variable using determinants. So you take the coefficient matrix, find the determinant of that, that's your denominator. And then if you're solving for x, you take your b vector, your values over here, you replace your x coordinates, your x vectors with the b vector, and then you take the determinant of that. And the ratio of these is what x equals. So this is pretty slick to do in your head for 2x2s. Because you can be like, oh, okay, I get a 4 minus a -3, so that's a 7. And then you can think, well, if I put that over there, I'm going to have a 7 times a 2, which will be a 14, minus a 0. So 14 divided by 7. So x is 2. So it gives you a pretty slick way to do 2x2s. Beyond that, it's not really useful because you'll spend a lot more time just trying to calculate 4 determinants of size 3 by 3. And that takes forever, and you may as well just do some row reduction and do it in a lot less work. So just the idea is the same to find y. You find that you have the determinant of the coefficient matrix as the denominator, and then you replace your y values here in the matrix with your b matrix, your b vector. So you have 2, 7, minus 1, 0. And so here you get 0 minus a -7, which is 7. And here I get 4 minus -3, which is 7. So y equals 1. So, okay, does that help?
Yeah.
All right, okay. You don't have to know Kramer's rule. One of the other professors this semester, a couple weeks ago, he was really pushing for us to teach it. And so I was like, sure, we'll teach it. I'll have you guys read about it. And he couldn't get to it in his class. And so he's like, well, let's not have it. So you don't have to know. It won't end up on an exam or anything. So, but it is kind of cool. And you might end up bumping into it later in another class. So sometimes some people will call this the most inefficient method to solve a system of equations. So you've got lots of time on your hand. It might not be too bad if you really only care about one value of your x, y, and z. Then maybe it might be worth it if you're at a 3 by 3. Maybe, I don't know. Okay, I doubt it. Okay, Another question that was asked last time was about idempotent. So, wait, Sam, are you recording? I'll just check.
Yes, I am recording.
Yeah, we're recording. Okay. All right, so this may have been on another problem or maybe coming up, nilpotent. Idempotent, the first part comes from my identity. So the same. Potent is power. So this is like the same power. Means you can take it to this power, you get itself. Like there's some identity transit. You have the power to become itself, or you put it to a power and it becomes itself. That's the idea of idempotent. Nilpotent, nil meaning zero, power. You bring it to some power, the matrix to some power, you get the zero matrix. So these are two special kind of matrices. This is a proof that a nilpotent matrix has a zero determinant. Okay. So just using properties of determinants, you take the determinant of both sides, but determine the zero matrix is zero, and then you pull the k out and such. Here, and you were supposed to find what determinants an idempotent matrix could be, and we'll come back to why. This is like using determinant rules. You can show, hey, it's 1 or 0. You get this equation. If you replace the determinant of A with X, you get this thing, and you just factor it down. It has to be 1 or 0. But there's another reason why this would make sense. We'll get to that. So, other questions? Yes?
If A is invertible, does that mean that the only invertible idempotent matrix is the identity matrix?
Not necessarily the identity, but it does have the a determinant of 1. But
Multiply both sides of the equation by A inverse, and you're left with A equals I, right?
yes, but I don't know if I'm not sure if it has to be squared. It could be idempotent matrices could be K, I believe. So it's not necessarily squared. So you might have to multiply it by 3 times or something. But I don't know. I thought there were it seems like there would have to be non-identity idempotent matrices, otherwise they wouldn't name them idempotents. Right? So, okay. Way to think, by the way. That's really nice. So, okay, other questions? Okay. Let's go to the slides here. We're going to start off with quick review. Remember, we talked about how you can use determinants to find areas and volumes, but they're areas of a parallelogram, volumes of what's called a parallel pipette. It's kind of like a squished, stretched cube. Okay. So if you had 3 points, here, or 3 points in R2, and you wanted to find the area of the triangle of those 3 points, then you'd have to find 2 vectors first. How would you find 2 vectors from 3 points? You subtract the points. Yeah, you pick a point, 1 point, subtract it from the other 2 points to make 2 vectors, and then you can take those 2 vectors, put them as rows or columns in a matrix, and you find the determinant. The determinant will tell you the volume of the parallelogram. If you just wanted the triangle, then what do you have to do? Divide by 2. Okay, so you subtract 1 point from the other 2 to get vectors, then find the determinant, divide by 2. There's a similar process here to find the tetrahedron. The volume of a tetrahedron, if you have 4 non-planar points in R3, then they make a tetrahedron. and you can find the volume of that. You do the same thing. You take 1 point, subtract it from the other ones, and then put the three vectors that you have in a matrix and find the determinant. But then you have to divide by 6. It turns out 6 of these tetrahedrons will take the volume of 6 of these to fill the whole parallelepiped. So it's not that hard to see why, I hope. So if you think of this, so the parallelepiped, you can just pick the area of the base times the height, right? The volume, sorry, it's the area. It's the volume of the parallelepiped that's the area of the base times the height. So we're going to think about this as the base. Well, if I take that base and connect it to 1 point, 1 vertex right here, then that's a pyramid. And the pyramid is 1/3 the base time, the area of the base times the height. Okay, it takes 3 of these pyramids to make the parallelepiped. The volume of 3 of those to make the large one. But the tetrahedron we have is half of that pyramid, and so we divided by 1/3 to get the pyramid. You divided by 1/2 to get the tetrahedron. The tetrahedron is technically a pyramid too, but you'll please forgive me for that. So if I have 4 points, I should take 1, subtract them from the others to get 3 vectors. Put the determinant, use the determinant to find the volume of the parallelepiped with those 3 vectors, and then divide by what? 6. Good. This does give us an area. You learned in calculus how to find areas and volumes of odd shapes. This actually gives us another method. It's pretty slick. Maybe if you already have coordinates of this, of the coordinates already stored in the computer, but you can pick any 3 points, make a triangle, find the area of that, pick any 3 more points on the outside, find the areas of those, and then just keep picking points on the outside and get as close as you want. You can just keep getting as accurate as you care about. And you can also do this for volume. Things like this in 3D modeling, this is stored as a list of points, and you could just start tetrahedrifying this thing and find the volume of each of those tetrahedron and then add them up. So, okay. Or if you're trying to find the volume of the lake and you knew the depth at different points, you could find a depth and connect 4 points and start finding volumes, and then you fill up the whole lake with tetrahedron. Okay, enough of me talking. Now that we've talked about that, you get to do it. So find the volume of the tetrahedron with these coordinates. And then there's a question about finding the determinant of this, the inverse and the transpose of this matrix. And then another kind of brain teaser there, trying to get our head around. So just quickly, if it wasn't clear from the screen, a tetrahedron looks like this. This is a regular tetrahedron. Each of the faces are the same size and shape, but a tetrahedron doesn't have to be regular like this, but this is tetrahedron-ish. All right. Yeah, I should have put a 0 in front of the 0.5, so it was clear that it was 0.5. So, so you might get. What do you get if you don't do it? What do you get? Was it 6?
I got
3? What did you get? 1. 1. A random whole number between 0 and 4. I don't know. Okay, so so here's someone's work. They subtracted. Looks like they subtracted 0, 1, 1. Is that the other one from the other ones, or 1, 1, 0? I don't know. So we get 3 vectors. They got the 3 vectors by subtracting one of the points from the other 3 points. Okay, and then they put them in as rows. It doesn't matter if you do rows or columns. Okay, that actually gets to part of number 2, because the determinant of a matrix is the same as the determinant of the transpose of the matrix. So it doesn't matter if you think about these as row vectors or column vectors. So in this case, the student did row vectors, puts them in there, finds the determinant. This one, smart here, if you're going to expand along one column, this is the one to do it. It's got 2 zeros. So, so you just have to pick the 1, eliminate the row in the column, and then you have 1 times a negative 1/2 minus 2 times a negative 2. So you get a negative 1/2 plus 4. So that gets you 3/2. But that's the volume of the parallel pipette. Okay, this we're after kind of one corner of the parallel pipette. You can imagine it like if you get, this is supposed to be a cube, but we're really after this corner that you'd slice off, and that's 1/6. It turns out to be 1/6 the volume of the entire cube. So, yep, you have to divide by 6 because we're just after the tetrahedron. So the way you can remember 6 is tetra means 4. Okay. All right. Okay. All right. Now I forgot where I was. Okay, so you get 7/12. Any questions? Hey, they're equal mod 2, right? Never mind. I had you guys skip all the modular sections of all the modular problems. So, okay, 7/12. Nice. So, questions on this?
So the 3.5 is the value of just the triangle, right? The pyramid being on the corner, right?
Nope. The 3.5 is the volume of the entire cubish thing. So that's called the parallel pipettes. These I kind of drew with 90 degrees, so it looked like they're 90 degrees. It's not necessarily that way. So yeah, they could be something like that. But yeah, so that 3.5 is the entire volume of the 6-sided thing. We just want the tetra-sided thing. So. So that's why we have to divide by 6. Okay. Other questions? I do need to repent. I said the book never talks about this. There is a section, I don't know if it's right after the determinant section or near the end of this chapter, that's about the geometric interpretations of the determinant, and then he does talk about volumes and areas and other things you can do with this in geometry. So I need to apologize to the author. Okay. Oh, number 3. Doesn't seem weird that if we expand along the first column, the circled numbers below don't change the determinant at all. 0, 0, 2, 1, 0, 4, 0, 1, 5. I could put in whatever numbers I want in here. Okay. If I make the 4 million, doesn't change it one bit. Make the 5 0, doesn't change it one bit. Doesn't that seem weird? Yeah. Kevin, do you want to give us your explanation?
If you imagine like what area the shape would be from two lines, it doesn't really matter. Changing those numbers is kind of like shifting it into a parallelogram, but the two sides that are opposite each other are really far apart, but they're still the same height apart. I don't know how to, I can't explain it very well, but it doesn't matter if we shift one of the lines. Like if you shift the top line of the parallelogram, you can shift it as far to the right or to the left if you want, but it doesn't affect the area of the parallelogram. It's the same idea.
Nice. Yeah, it's easier, much easier to see than in 2 dimensions. Oh, where's my blue? Blue. So I drew out these 2 vectors. There's the parallelogram that the determinant of that would represent. It doesn't matter, you know, doing the determinant doesn't matter what this is, right? If I plugged in 5, then what would I get? You know, 1, 2, 3, 4, 5. I'd get this vector. But then the area of I'd be trying to find is of that. But aren't those the same? Yeah, because they're a parallelogram with the same base and the same height. It's still up 2. So this value here or these values here are moving a point around and keeping it the same distance away from a base, but it doesn't change the volume here or the area there. So that's the way to think about that geometrically. So nice. Okay. Sam, I'm fighting with you for the mouse. Okay. All right. So, we can use determinants to find areas and volumes, but they also represent something else connected to transformations. So if you're thinking about a matrix multiplication as doing a transformation, especially a transformation on an object, then the determinant in R2 tells you how much the area of that object is scaled after you do the transformation, okay? Or by the transformation. And in R3, it tells you how much of the volume of that object is scaled by that transformation. And in R4 or R5, the hypervolumes are scaled. So if you have a determinant, well, so like over here, if I've got a matrix that transforms this triangle into the green triangle into the blue triangle, then about what would the determinant of that matrix be? How much does the area of the green get scaled to the blue? Talk to your neighbor. Think about just approximate it here. All right. So thumbs up if it's greater than 1, thumbs down if it's less than 1. So thumbs up if we're going from the green to the blue. So thumbs up if the determinant's larger than 1, thumbs down if it's less than 1. So good job. It's larger than 1 because the area gets larger. Okay. So I heard a lot of people say 2, about 2. That seems about right. So it's about twice as big. It might be a little more than 2, but close enough, right? We're about twice as big or 3 times as big, something like that, in area. So the determinant of that transformation matrix would be that scale factor. Okay. Not the scale factor of the edges, but the scale factor of the area. In R3, it's the scale factor of the volume. It's how much, like, if you think of a cube, a unit cube, and apply the transformation to the vertices of the unit cube, you'll get a parallel pipette if it's an invertible matrix, and that'll have a volume, and that volume is the determinant. Okay. What about the sign? So this actually is only for absolute value. We only care about the absolute value here. It could be positive or negative. What happens with the negative determinant? It changes the orientation. Don't think of orientation as like which direction it's facing. Not that kind of orientation. The orientation in terms of which way you go around, which way you trace the object. So here A, B, C, back to A goes counterclockwise. But a change in orientation means that if you go around the transformed A, B, and C, you go the other direction. So orientation changes if there's an odd number of reflections. So just FYI, one way to think of it. You don't always know that just from looking at the matrix though. But okay. So with this understanding, here's another task for you. Why would the determinant of AB be the determinant of A times the determinant of B? We just talked about what the determinant represents geometrically. So think about why would the determinant of AB be the same as the determinant of A and the determinant times the determinant of B? So think about that and talk with your neighbor. All right. Let's come back together. Okay, remind me your name. Josh. Josh is going to give us his explanation.
All right, so like if you have a transformation, and maybe it changes the unit square to some sort of parallelogram way of area like 2.4, right? So
Okay, so for those online, because they can't hear you, so you're saying suppose you got the unit square and you apply the transformation of A, we'll say, and it takes the area of A to an area of 2.4 on some transformed object. Okay.
Scale any area theoretically, right?
2.4 times the original area. Yep, good.
And so then if you're to do another transformation B, that does something, say, like increases the area by 3, right? But you already did the first transformation, so your area increases 2.4. So then just multiply them together, geometric interpretation.
Okay, nice. So B is a transformation that says maybe it transforms the area by a scale factor of 3. but you've already transformed it by 2.4, so you get a 2.4 scaling and then another 3 scaling. So the total scaling should be 3 times 2.4. So that's the idea of this. That's one way to make sense of why this should be true, and the determinant of AB should be the determinant of A times the determinant of B. You're applying one transformation, another transformation. You can also think about it in terms of orientation. That's the other, like what happens with the sign? Well, if one changes orientation and the other one doesn't change the orientation, then you'll still end up with a negative because you have a negative determinant times a positive determinant, and you'll get a negative determinant. If they both change orientation, you'll be back to the original orientation. Orientation in 3 dimensions and 4 dimensions is kind of hard to think about. You have to think about like turning a parallel pipette inside out. It's kind of weird, or a 3-dimensional object inside out. But you guys can try that. Okay. I forgot to do 2. We skipped ahead. But you know, if tetra means 4, you know, we can skip 2. All right. What's the determinant of the inverse of the following matrix? Okay. The determinant of this matrix is 15, right? It's upper triangular. You just multiply down the diagonal, you get 15. What about the determinant of the inverse of this matrix? Yes. 1 over 15. Why? So now that we've talked about what the determinant represents in terms of transformation matrix, explain to your neighbor why it would make sense that the inverse of a transformation would have a determinant of 1 over the original transformation. All right. Okay, so this is, here we can think about BART, right? Our picture that we transformed quite a bit. You can think about the transformation we do to BART, and if we scale them up by a factor of 3, then the inverse transformation would have to take that picture that's 3 times as big and shrink it down to 1/3 the size to get it back to the original. So the inverse transformation would have to be 1 over the determinant. And it could go the other way, right? You could scale it down to 1/3 first, 1/3 the size, 1/3 the area, and then the inverse transformation of that would have to scale it up by a factor of 3. So, so if you find the inverse, you find the determinant of 1, now you can easily calculate the determinant of the other one. This is another reason why non-invertible matrices do not have an inverse, because a non-invertible matrix has a determinant of 0. So you'd have to have a matrix with a determinant of 1 over 0, which is undefined. So, okay, what about the determinant of the transpose of this matrix? If I transpose this, what's the determinant? Same thing, still a upper triangular. It's true in general. Transpose doesn't change. Because we can choose to expand along any row or column. If we had a matrix and we expanded along a row, you transpose it. Well, just expand along the column. Okay, expand along a row. Yeah, expand along the column after you transpose it. You're going to have the exact same mathematics. Yes, Andrew.
It seems like the determinants, when we're using determinants, we can use normal math laws instead of like matrices math laws. Like you can multiply the determinant of A times the determinant of B, switch it around, and it doesn't really matter. You can take the inverse and it's 1 over the number like it is in other math. It seems like when we work with determinants, we can use like algebra-based or calculus-based ideas like multiplication, like just going across.
Okay, so Andrew said, for those online, he said, seems like with determinants, we can just work with the mathematics of real numbers. You can multiply them, right? The determinant of AB equals the determinant of A times B. You take powers of them. I can't remember the other one you said. But they are real numbers. The determinant is a real number. So we can use the mathematics of real numbers on those determinants. But it doesn't generalize perfectly, because the determinant of A plus B is not necessarily the determinant of A plus the determinant of B. So it doesn't always work. But the determinant itself is just a real number. Well, I mean, it could be, the determinant could, if you have real numbers, if all your entries are real, then the determinant's going to be real. So yeah, so it's just going to be a real number. And so we can use real mathematics, the real number, real line mathematics to work with the real numbers. Yes.
Before, like you have a matrix and you can't just multiply it out normally, but if you have a determinant of that matrix, then it's a scalar or a real number. Now it's a lot simpler.
Yes, it is. It's a lot simpler. So speaking of simpler, let's move to, okay, last thing, we got 6 minutes. So we have some intuitive idea now about why the determinant of AB should be the determinant of A times the determinant of B. Now let's see if we can prove it using elementary matrices. If you knew that the determinant of two elementary matrices multiplied together is the determinant of the first times the determinant of the second, then can you prove, your task is to then prove the determinant of AB equals the determinant of A times the determinant of B. The determinant of elementary matrices is easy to do. There's only 3 of them. There's only 3 cases. Swap, so that means your identity is going to, the determinant's going to be a -1. Swap from the identity, you're going to get a -1. Multiply one row by k, you're going to get k, because it's triangular. Add one row to another row. Add a multiple of one row to another row. I didn't do a multiple. Doesn't matter, because it's still triangular. You just multiply down the diagonal, doesn't change. You get 1. And we could look at each case and take each possible combination and multiply them together and show that the determinant of 2 of those multiplied together is the same as the determinant of the 2 and then multiplied. But you can just work with it. You just assume this is true. Assume this part is true. Okay. Then now your task is to prove the determinant of AB equals the determinant of A times the determinant of B. I'm giving you a hint. Break it into 2 different cases. Okay. So see what you can come up with. All right. We have the proof of of case 2 going up over here, but let's talk about case 1 because we're running out of time. So if either A or B is non-invertible, then what do we know about the determinant of a non-invertible matrix? It's 0. Okay. If you think about that in terms of a transformation, in R2, you get the transformation takes everything to a line, so you don't have any area, or down to a point. And in R3, it would go down, the volume would go down to a plane, which doesn't have any volume, or a line, which doesn't have any volume, or a point, which doesn't have any volume. So, so the determinant's going to be 0 for at least one of these, so that makes the right side 0. But what about A times B? If one of these is non-invertible, what about AB? Yes?
So if you think of both of them as being combinations of elementary matrices, it means that the non-invertible one is going to be some combination of a non-invertible matrix times a bunch of elementary matrices. So like no matter how many row operations you do to a non-invertible matrix, it will still be non-invertible, which means that AB is a non-invertible matrix.
All right, nice. Okay, so so I'm just going to summarize for sake of time, but yeah, you gave a nice argument on why if you have a non-invertible matrix times any other matrix, whether it's invertible or non-invertible, it is going to be non-invertible. Okay, if you think in terms of transformations, if one of the matrix reduces the dimensions in the transformation, doesn't matter what the other matrix does, you can't get scaled back up to the full dimensionality. Okay, like the rank. Once you get down from full rank, no matter what you multiply by, you can't move up to full rank. Okay, so the determinant of that will be 0 also. So they're both 0. So that proves case 1. Yes? That's right. Yeah, so the argument before said you'll have a non-invertible elementary matrix. Technically that's true, but he meant a non-invertible matrix multiplied by elementary matrices. That's right. Yep. Once you have a product, if you have a bunch of product of matrices and one of them is non-invertible, it doesn't matter what the other ones are, that product's going to be non-invertible. Okay, we have 30 seconds. So if it's invertible, then you can write each of these as a product of elementary matrices. And so if you know that your theorem works for elementary matrices, you can do the math and you can rewrite A and B as A times B, which is just a product of a lot of elementary matrices, and then the determinant of AB is the determinant of all of that, but the determinant of the product of a bunch of elementary matrices we can already chop up to be the determinant of the first and times the determinant of the second times the determinant of the third. And then you get all of the ones that are A and put them together, and so you can get the determinant of E1, E2, E3, etc. Determinant of E4, E5, E6, etc. And this is the determinant of equal to the determinant of A. This is equal to the determinant of B. There. So we used what we know about elementary matrices to prove that, hey, the determinant of AB, that is the same as the determinant of A times, that's a multiplication, times the determinant of B. All right, have a great day.